You ready to learn like math?
Yes.
Oh, yeah. Hey, normally I would say this helps for your benefit. Do them, don't do them, it's up to you. But this historically is harder for students, and so I would, if I were you, I'd be with it. Right? So here we go. Also, I'll say this: people might run long, and so that homework that is due today probably won't be due today. You probably won't get to it. So again, don't be finishing that homework, ignoring it. Just pay attention. Let's just do it. All right? Ready? All right, here we go. So, the idea of a Riemann sum, this will be a little simplified. The true Riemann idea, the Riemann hypothesis, is really a little more complicated because it deals with unequal subintervals and modulus and all this stuff. This will be a little cleaner. If you become a math major, then you're going to have a little harder run of this. But this will be a very good primer on it. So, check this out. We have a parabola from 0 to 8, and we're using 4 rectangles to estimate the area of the curve. Now, obviously this is going to head towards integration, and integration has a ton of applications, and I'll get to all those applications. But for now, just keep it in the back of your head that all this symbol pushing has a point and has a use. It's not just symbol pushing, right? So, my idea here is something like this. If you're visual, great, go for it. But if I'm using rectangles, let's start with saying area by 4 rectangles would look something like this. Now, I might bypass that step a little in a second, but for now, that's the big idea. If they're equal subdivisions, then what can I do? I guess I could draw a picture just for visual. Really, really, really spread out. Okay, if they're equal subdivisions, then doesn't that mean they have equal bases? Yes? So, factoring out a common base leaves me with 4 different heights. The heights will vary with respect to the curve. The base is a width, I'll call it delta x, where there's a gap. It could be delta y, but let's not even go there. We'll call it delta x today. The heights are surely function values or y values, so it'll be f at different values. I'm going to call this the first, the second, the third, and the fourth if I'm using 4 rectangles. Cool? So when we go to estimate area under a curve, it's typically something like a sum of bases, which are horizontal delta x's, and heights, which are x's at different points. I'll represent my counter width. I don't like to use n because n usually represents the number of rectangles, so that'll usually actually be here and in here, so I'm going to use I for a counter. Now if it's 4 rectangles, then I'll go from the first to the 4th. So remind me, what does delta x stand for? The base is of the rectangles, and F stands for the height. All right, here we go. If I use, I hope you're able to get this on better than I am. If I use left hand, then let's go with a base of, should I use, yeah, let's go back to this way. I think we'll build up to the summation notation. If I use left hand then and 4, what's the delta x in this case? 2. And the heights, if I use left hand rectangles, then the first height is f at 0 or f at 2? F at 0, then f at 2, then f at 4, then f at 6. In this case, left hand rectangles seem to be underestimating. Why is that? What's special about this curve that makes for an underestimation? Left-hand rectangles seem to underestimate when the curve is it about concavity or increase? When we say increase, too bad. Nobody's, okay, one person's right. Excellent. It's about increasing. Okay. Concavity is not an issue. I don't care if it's concave up or concave down. If it's concave up and increasing, underestimate. If it's concave down and increasing, still underestimate. Doesn't matter the concavity. Doesn't matter. Increasing, decreasing is what matters. Concavity will matter when you use trapezoids. Did you use trapezoids next week? Okay. Well, we'll do trapezoids. They're the best estimator. They're a good estimator. I don't want to say best. Simpson's rule is better. But the point is, it's about increasing, decreasing, not concavity. All right. So that makes sense. If it's increasing, the left will be less than the right in nature. So I'll get an underestimate. What do you get for? Actually, we could get in there. Could you give me that estimate if you wanted to?
Yeah.
Yeah. So let's not waste our time with that arithmetic. Because unless you're not clear what you would do, then let's move on. Are we cool? Yes.
Isn't that supposed to be at zero first?
Assuming you called this A, which it wasn't. Learn how to read. Sorry, yes, that's B, that's right again, yes? So Emma, since you're so smart, what is left hand, please?
F of 0 is something to
Chip off the old block right there. Boom. Okay. Yes, correct. Sorry about that. All right. What about midpoint? Base, would it change for midpoint, or would it still be 2? Still be 2. What are the heights at? F at 1. Now, it's the midpoint of the x, so halfway between 0 and 2 is 1. Continue, please. F at 1, 3, 5, and 7. Which of those 3 would probably be the closest to accuracy? Yeah, the midpoint, you have a little above, a little below, and you'd still be off, but it'd probably be closest. In terms of the least to greatest, arrange them from least to greatest.
Area?
That area, your estimates. What would they come out? What would be least? Left, right, or mid? Left, then right. All right then. Say we had this happened, especially back in the day when they didn't have calculators. All right. So if you had something that was an ugly function, like a square root function on 0 to 16, it wouldn't make sense to use 4 equal subdivisions because that would mean square rooting 8 and square rooting 12. We don't want to really go out there. So instead, we would do unequal subdivisions based on where clean numbers in the square root function are. So what would be good numbers to use? 1, 4, 9, and 16, right? Now, if I'm using unequal subdivisions, then this step here, the factoring out the common base, is it there? No. It is not there. And so we have to either go to or keep a separate calculation, something like that. Let's go with left hand rectangles. The first rectangle, what's the base? 1, and what's the height? 1. Now, I expect you, when you do this, to communicate where you came from. So the 1, I don't really need to know where that came from. You don't have to tell me 1 minus 0 is a base of 1. This, I don't need to see, although I had a professor who was nuts about that. I'm okay with you making that calculation. I do want you to tell me where you pulled the height from. So the first height was F at, if it's left hand, 0. Okay, plus, so here's my first rectangle. Here's my next rectangle. It's 3 wide from 1 to 4, and I'll have a height at 1. F at 1. Okay, so it's a base of 3, which comes from 4 minus 1, times F at 1. The next rectangle, base and height, please. 5 times F at 4. And the last? 7 times F at 9. Okay. What about the, I'm not doing midpoint here. Let's do right hand. First, actually, the bases, will they change? they'll be the same, 1, 3, 5, and 7, but what are the heights? F at 1, F at 4, F at 9, and F at 16. And right-hand rectangles would over or underestimate. Over because the curve is increasing, positive slope. All right, you with me? Okay, now then, so say you're in Fremont shoes and you have no calculator available, and you want to get a better estimate. What could you use in here? What x value could you use in there? The square root is nice too. You want more precision, you need more rectangle. Come on, people take the box, people. Give me a number between 0 and 1 you could square root. What? Give me a fraction. Give me fractions, people. 1/4. Could you square root that? Boom. What else? 1/9. Boom. What else? 1/16. Just go on with more of the same. How about 4/9? 4, 9, 16. Right? All those are good. Yeah. Okay. What else? What about between 1 and 4? If you wanted more precision, what could you use? 9 fourths. That's where it's nice and agree. Okay, so that's how they got more precision. They thought of rational numbers of perfect square. Okay, moving along. Estimate the area using 4. Where did I put this in here? So table practice. You need table practice. I thought I wanted something. Oh, never mind. It's good. Okay. So left hand. If it's 4, then what's the delta x? 4 rectangles. Each delta x is 2. How did you find that? 8 minus 0 divided by 4. So you could say that delta x comes from the right edge minus the left edge divided by however many rectangles you want in this case, yeah? Okay, so delta x comes from the width of the region divided into some number of chunks. Okay, so the delta x times f at different x's. Or delta x. Is delta x common in this case? Yes. So, left hand. Give me the f values. F at 0, f at 2, f at 4, and f at 6. Just like the other one. I should have made it different. All right. What about midpoint? F at 1, f at 3, f at, and f at 7. Boom. What about right? F at 2, 4, 6, and 8. All right. Now, if you're thinking, I don't think this is hard at all, I agree. We're warming up slow. It'll get harder. Moving on. Okay, here we go. I want you to express an area under a curve starting at a left endpoint 0. That's a big helper to you. When you start at 0, it's much easier than when you don't start at 0. I'll tell you that. In expanded or summation notation. So, what if, in this case, instead of giving me 4 right-hand rectangles, I'm asking for some general nebulous n right-hand rectangles. I want to think a little more abstract. So I have this region here, and it's 8 wide, and I'm dividing it into n chunks. Kind of working towards a general, like a program, a computer program that would work for any input value. So, first let's find delta x. What's delta x? B minus a over n, or 8 minus 0 over n. Each width would be 8 over however many subdivisions you've decided. Okay, that's the base of each rectangle. All right. The first height, if I use left hand, oh, right hand, excuse me. If I use right hand, then what's the first x I put into the function to get my height? N? Okay, where am I starting? 0. How far do I go each time, or what's the delta x? 8 over n. And so I ask you again, what's the first x I put in? 8 over n. Oh, great. The second x I put in is 16 over n. Now, this is the hard part. You want to simplify it. 16 over n makes sense. Don't call it 16. Call it 2 8 over n's. The reason is when you go to summation notation, you want it to have a counter element. So there's 2 8 over n's, 3 8 over n's, all the way till the very end. How many 8 over n's are there? 8. How many, sorry? Not 8. N, yeah. If you have n, 8 over n's, how wide is it? 8. Yeah, so the last one is the nth 8 over n, the last 8 over n. Now, if we then were to do this in expanded notation, it would look something like the area is approximated by 8 over n, that's the delta x, or the base, and the first is f at 8 over n, then f at 2 8 over n's. Make sure you write 2 times 8 over n, not 2 8 over n, because that looks more like a mixed number, you know what I mean? So 2 times 8 over n's. Or you could write as in the numerator, f at 3 8 over n's, so on, through the last, which is the nth 8 over n. That's just terrible if I went into my... You with me? Are you with me? All right then. If you go to write this in summation notation, you want the counter. You want to identify the counter. The counter is right here. How many 8 over n's? You have 1, 2, 3, n. So if I were to do this in summation notation, or with the old sigma, don't you dare call it the big E. It's not a big E, it's a big S. Sigma is a Greek S, not a Greek E. It's an S. And so the big S is, well, we still have that delta x there, it's 8 over n, and it's times f at, now, 1, 2, 3, what should we call our counter? Let's use that. Okay, you could use K. A lot of books use K. Why not use N? N's taken. What's N stand for?
Number of triangles.
The number of rectangles. The number of rectangles. The number of rectangles. Okay, so N's taken. You can't use N. How many? What's the counter start and stop? Look in your work. What's the first I? 1 and the last I. N. That's nice. If you wanted to go more specific and actually use the f of x, we could put in f of x and say this is 8 over n, and instead of 8f of I times 8 over n, I could write blank squared plus 1, because that's the function, and in the function, say, the I of 8 over n. Cool? Now, this direction is the easier way. The harder way is this way, is when I say, here you go, here's a big expression. What is it? Well, you're going to have to say, all right, well, first of all, it must be a region that is 8 wide, and the function must be something like x squared plus 1. And you would also have to know that it's starting in 0. We'll get to that in a second. Okay, that's the part that students have to practice quite a bit to get there. Okay? would you please try it on your own? Write an equation to estimate the area, and when I say equation, I mean summation notation. To estimate the area under that using n right hand rather than oh, shucks. Did you see a problem already? You should see a problem already. What's that problem? Tell me what the problem with this is, why Mr. Kucinich.
Can't start at 0.
Yeah, 0, is that in the domain of this function at all? It is actually not. So let's call this x plus 1, sorry. My bad. How are we doing? You get something like this. You agree? Okay, that's right. This is left. So it would start at, say again? I would start at 0. Okay, perfect. And where would I end? N minus 1, because instead of getting all the way to the right side, if we're using left-hand rectangles, then we're starting at no 8 over n's. We're starting right at the left edge, and we're not going to the nth side. We're going to the n minus 1. So for left hand, it would go, oops, this should stay 1. It would go from none to n minus 1. So if it asked you to interpret that, you would also have to be saying this. This is an estimation of the square root of x plus 1 from 0 to 2 using left-hand rectangle. Okay. Speaking of which, let's go backwards now, shall we? This expression is an expression for finding the area under something from somewhere to somewhere using, I'll give you that it's right. What's the function? 2 minus x squared. You could call it, there's no name for it, I'll just call it f, but 2 minus x squared. Over what interval? That's what I said, cube. Okay, over what interval? 0 to 3, yes. Okay, 0 to 3, excellent. It's right hand, yes. Okay, try the other one. What did you say for the function? 2x cubed plus x. You can see you have 2 input places here, and the region is from 0 to 5. Excellent. Okay, good deal. All right, now these are all cases where it's starting at 0, and that makes things harder. When you start at 1, or sorry, easier. When you start at 1 or any other non-zero number, things get a little more complicated. So, let's express an area under a curve at a left endpoint of something besides 0. If I have that same curve, x squared plus 1. I draw it really wide, obviously not drawing to scale, from 1 to 8. Then, and I use right-hand rectangles. First of all, what's my delta x now? A width of 7 divided into how many chunks? N chunks. So each chunk or each width is 7 over n, which obviously could be a lot of things depending on what n is. Let's just say it's this much. This x, is it 7 over n? It is not, because we didn't start at 0 and go over 7 over n. We started at 1 and went over n, 7 over n. So what is x1? It is 1 plus a 7 over n. What's x2? 1 plus 2, 7 over n's. x3 is 1 plus 3, 7 over n's. What is x sub n, or the last x in? 1 plus n, 7 over n's, which does simplify to 8. We're all good. You with me? Okay. Drawn at the right-hand side. Like that. Da, 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 da. Okay. So if I were to write an expression, we would have the summation of, what's the delta x, or the base of each rectangle? 7 over n. The height is f at a little more to it than that. If we start at 0, then x sub whatever I is just how many delta x's you went over. But if we start at some other number, let's just call it a general A, then the x's will depend both on where you start at A and how many deltas you go over. So x sub I will be A plus some number of delta x's. So in this case, we're talking an A, or a starting value of 1 plus I deltas, which delta is 7 over n. Okay? What I do I start at? I starts at, how many 7 over n's do I start at? x1 is 1 7 over n. And so it starts at 1 and ends at n, but if it were left-handed, it would start at, oh, I'm so disappointed in you. If it was left-hand, you would start at 0 and go to splendid. All right. If I wanted to get more specific, I wanted to say the multiple choices didn't have that F notation, they were more specific, then instead of F of, they might have blank squared plus 1, and actually showing 1 plus I 7 over n's. We? Are you with me?
Yes.
Okay. Try this one on your own then, please. Later in here, we're going to talk about that frequently. You have something like that going on. Right? Questions so far? There we go. Let's move on. Gradually get a little harder. Oops, or nothing. Still nothing. Okay, here we go. Going backwards then. I give you the summation, you tell me the function. What about this? What do you reckon the function is? X cubed. And what's the region? 2 to 5. Okay, now pause here. Pause here. There actually are an infinite number of solutions to this. That's one, the most logical possibility. What else could the function be? Actually, let me go here. If I told you the region was this, would the delta x still hang true? Yeah. What would the function be? 2 plus x quantity cubed, right? How can those have the same area? They seem so totally different. Well, x cubed looks like this, and 2 to 5 would be this region, yeah? X plus 2, how is it shifted? Right or left? Left 2, and the region is? That's logical, it's the same, right? Okay. Now, wouldn't it stink then if you actually had a multiple choice where they had A, B, C, D, and E, and they said 4 of these are correct. Which of those is not correct? That would make things a little more difficult, but okay. So try this one on your own, please. Give me the most logical solution. Let's go with the most logical solution, but I'll take anything. If you have something else that you want to throw out there, fine with me also. Go for it. ¿Listos? KSO function. ¿Cómo se dice function en español, por favor? You're just making it up. Really? Function? Function? Now you're just really making it up.
No,
You just
that's
said
actually what it is.
I'm going to go ask her after. I'm going to. ¿Cómo se dice natural log en español? You better look into that. All right. Function is, what'd you say the function is? 4 plus x would be a logical one. If that's the case, then what's the region? That would be 0 to 5. What if I told you that the region was 4 to 9? Actually, shoot. Okay, 4 to 9. And what's the function? Natural log of x. What if I only told you this? Negative 2 to 3, because it's got to be 5 wide, right? And the function? X plus 6? Do I agree with that? Let's think of what the sum here has to be. Okay, that has to be 4 in some fashion, yeah? So, yeah, 6 is right on. 6. Okay. Now, think like something like this. If I started at, let's actually go here. This graph, wouldn't that be left 4? Oui? Yeah. And 0 to 5 would be here. How about this guy then? It would be left 6. And so, then in that case, actually, let's go back here. Wasn't the gap from the axis to the start of the region 4? So if they're telling me the start of the region is at -2, then doesn't that distance still have to be 4? And so that's why, yeah, -6. That's going to be the same value. Okay. Still confused? Okay, sounds good. That's fine. I'm not 100% sure my mind's around it completely yet. Don't we know that the starting point of the region is 4 units from the 0 here, yeah? Is that true? Do you agree with that? Okay. So start by thinking, where does the graph start, or the axis or the asymptote is -4, and I need to start my region 4 units over. All right. Now, if this case the asymptote is at -6, and I need to start my region 4 units over, then don't I have to start it at -2? All right. I don't want to get hung up on that. We'll practice that later. Don't sweat it if your mind's not around it yet. All right. Here we go. There are some great formulas. I used to make people do these on their own, but they're hard to develop. But gosh, it's really fun to develop these formulas. This one, gosh, this one's fine, but this one's super famous. Let's go through this. If you add a bunch of constants n times, then wouldn't the total just be whatever the constant is, how many times you had it? Multiplication, right? So that's makes sense, yeah? Okay. Think about how hard these would be to come up with. This says add 1, starting at 1, add the next greatest integer, the next, through n. Now, that would take some serious thinking, yeah? And that is actually a really famous formula. Do you know the story behind that? No? All right, this is a great story. So there's a formula for that. How can you do it? Well, the story goes back in Germany about 300-400 years ago. Some 6 or 7-year-old teaching 7-year-olds in Germany. They knew addition, and he was lazy and didn't want to teach that day. So he just said, you know what, kids, today I want you to add the numbers from 1 to 100. And he kicks his feet up and thinks, okay, now I'll be able to read my paper. But not 20 seconds later, this kid takes his slate up. They didn't have paper, they used a little chalkboard. He brings his slate up and he says, there you go. Done. And the guy said, kid, I didn't do the problem. I made my paper. No, I'm done. That's right. That's it. Done. So this kid was 6 years old, actually 5 years old, because he was accelerated. And the teacher says, all right, adds the numbers to the dumb teacher. And he finds that the answer was indeed correct. It is something like this. Like, I don't know. How do you do it? How do you do it so fast? Obviously, you didn't have to know this. So you did it in 20 seconds. How did you do it? I'll give you a hint. Rainbows. Does that help you? Rainbows. It's all about the rainbow. What? Yes, the rainbow. What does that add to? What does that add to? What does that add to? Each sum is 101. How many sums are there? 50. 50 sums times 101. Oh, geez. 5,050. That's urban legend, but I believe it's true. That kid was 6 years old. That formula was well known forever, but he didn't know the formula. He did it on his own like that, 20 seconds. Now don't feel bad, because you are not as smart as a 5-year-old. because that guy was the greatest mathematician of all time, right? In my guys. One of my German Germans. This guy was so stinking famous, he had his doctorate by the time he was like 13, 14, and he got so sick of coming up with new theorems, he would just send them out to his friends and say, yeah, you just make credit for that. He's just mind-blowing, genius. Anywho, this formula comes from taking the sum of how many numbers, actually, let's go here. Wouldn't you say that the 101 comes from taking the number of numbers plus 1? And then how many pairs is the number of numbers divided by 2? And so this is the sum of each pair times the number of pairs gives you the sum, just like that. So that's how to find the sum of integers. This is where things start to get a little more complicated. 1 squared plus 2 squared plus 3 squared through any number of squares. That's starting to get rough. You better be on game here. That I played around with for about 4 hours. It's just what I do. And I came up with it, but it's pretty hard. It's pretty, if you have free practice sequences. Where'd it go? Did you say no? Okay. All right, then, it's not an assignment, but gosh, if you want the mental game of it, it's pretty great. And then the cube is also pretty great. 1 cubed plus 2 cubed plus 3 cubed and so on. It's kind of cool, though. Look, I mean, square to sum first degree numbers. Cube to summarize second degree numbers. Fourth degree to sum cube numbers. There's some calculus in there you can use. It's pretty great. All right. These are formulas, though. I do not expect you to memorize these formulas. That's a waste of your time. I'll always give you those formulas. Don't worry about memorize. What? How did that do that? I didn't even know it did that. How do you get rid of this thing? What? Oh, you're so smart. Oh, you're smart. You're the next Gauss. You're like a genius. Okay. I saved that VNN for later. All right. So we're going to use those. Now, if I want to get into the perfect area estimate, then rather than use 4 rectangles or 6 rectangles, I want to use infinitely many rectangles. And I get infinitely many rectangles by letting what go to where? N go to infinity. All right, now that's super duper, but these guys aren't functions of n, they're functions of I, so I really need to dump the I, and that's where these formulas come in. It's not just fun stories. I'm going to use those in a second. So check this out. Say I wanted the perfect area estimate there. Let's start by writing this in summation notation. What's the delta x, please? 4 over n. And f at starting at 0 is the nice case. And f at, what are the x's at which you will find the heights? What are x sub i's? They come from the starting plus how many deltas you've gone over. So f of 4 over n, how many times? I times, okay? And if I'm using right hand, I'm starting from 1 to n. Cool? If I use the function then, it's something like instead of f of, it's 4 over n I cubed plus 2 4 over n i's. I use the function and plug those x's into that. You with me? All right, now. The idea is to isolate something like I cubed or I because I have formulas for those. I can say, oh, the sum of a bunch of cubes is that guy. Or the sum of a bunch of i's is that guy. Before I can use those formulas, though, I really have to isolate those. Now, this kind of goes just to, there's rules for integrals, there's rules for derivatives, there's rules for summation. First, I can take a 4 over n out. Because that's not involved in the I counter, it's a common factor, I can pull it out, no problem. You will, by the way, cut a lot of these steps I'm about to do out. I'm just trying to go slow the first time, all right? Likewise, you could split that sum up into two separate sums. So you can have 4 over n times the sum of many 4ni cubes, and then also 4 over n times the sum of many 2 times 4 over n i's. I split the sum into separate sums. It's all adding, so yeah, that shows a lot. You with me? Playing a little fast and loose with my summations because in the interest of time. All right, now, this guy. Again, that 4 over n, it's cubed, but it's not an element to the counter. And so I can pull that 4 over n cubed out, leaving me with just what's the sum of 1 cubed plus 2 cubed plus 3 cubed plus n cubed. It's just, it stays the same, so it's just a greatest common factor factored out front. Same goes here. I can pull 2 out. I can pull, the 4 over n still there, and I can pull another 4 over n out, leaving me with just the I in the counter. That's allowed. That's the thing. All right. Altogether then, I have something like 256 over n to the 4th. And this sum of 1 cubed plus 2 cubed plus 3 cubed plus n cubed, there's a formula for that. Rather than adding all those cubes, the formula is, dependent on the n point, is that it adds to n times n plus 1 quantity squared over 4. You follow? At the other one, I got 32 over n squared times the formula, the 5-year-old formula, n times n plus 1 over 2. Now, that then is a stripped down formula that I could use to find any kind of estimate. If I said, hey, give me an estimate using 2 rectangles, then I could just plug in an n of 2, and boom, I've got my estimate. I could say, hey, give me an estimate with 20 rectangles, and I could plug in a 20, and boom. But even better would be that I could then take, if I call this a sub n, or area as a function of n, I could take the number of rectangles to infinity and get, what would that formula, oh shucks, we're out of here. That's a good start. But you could see with n behavior how you could find, boom, perfect area. We'll talk about that later. We'll finish. Nothing's due. Have a lovely day. If you want to see how you did on the first page, fill it up here, and I can show you how you did on the first page. All right. I need these back, by the way, if you have all. You can get it to Miss Smith or me right here. If you're done, just put it right here on my folder. You're done, put it right there on my folder. Remember, terrible. Not take it, put it back in my folder when you're done. So bad. When you're done, put it right here. Hi. I need it back when you're done, put it here, please.
Did Shiloh leave her calculator here?
Over there, the one not in the step, not in the step.
All right.
Make sure you get it back to me, do not keep it, please. Thank you. you're so close to perfection.
It's a negative, not a positive. Just need 1/4 left. I'll look at the.
Thank you. Oh, I forgot to pause it. Next.